now we will begin. The place where we stopped was writing down the expression for k, which is beta z. That is where we ran out of time, all right. And the expression that we could write for the electric field is, oops, E naught e to the minus j beta n hat dot r. So, we had defined a problem statement like this, where you have a point in space, all right, and you have a plane wave front. You are having the direction of the normal, a vector connecting the point on that plane to the origin, all right. You have to take the dot product between r and n, all right. So, you are taking projection of one vector on the normal and trying to figure out the equation for the electric field. Okay. So, last time we had seen how to write down the k vector, all right. So, you will have beta multiplied by cos phi x x hat, cos phi y y hat plus cos phi z z hat, all right. And in the case of a z directed wave, all you will do is you will change phi z to 0 and the remaining angles to pi by 2 and pi by 2. These two become 0 quantities, so end up with beta z hat, okay, which means that one could start writing down the expression for the electric field over here. So, you could say that this e to the minus j beta okay, beta n hat dot r vector. So, here we can say that the beta n hat that we have found is k, right. Beta is a constant, n hat is the normal to the surface that we have already found, that is the k. So, you could always write this down as k dot r, all right. Now, r is going to be x x hat plus y y hat plus z z hat corresponding to x y z coordinates of that particular point. This is how you will write down the expression for a plane wave in an arbitrary direction given a coordinate system. So, you will try to find out k, which is a point, all right, which is a vector joining the origin and the point on the plane that you are going to be talking about, that will have x x hat plus y y hat plus z z hat. And then you are going to be dealing with finding out k, which is going to be simply beta times n hat. So, you have to find the normal to that plane and then you have to multiply it with a constant, right. And so, when you take this expression, this is giving you the expression for a plane wave electric field, right, traveling along a particular direction given an arbitrary coordinate axis. Okay. And in order to verify, what you can do is you can substitute k to be beta z hat, r for example, you can take a plane which is perpendicular to the z direction, all right. That is how your phase front is going to be for a z directed wave. The phase fronts are going to be like forming slices in the z axis. So, you can take a point, for example, z hat, right, x x hat plus y y hat plus z z hat was the point corresponding to r. You can simply take one of the points to be z z hat, okay, right at the center, x equal to 0, y equal to 0 and z, and you will end up getting E naught e to the minus j beta z. Okay. So, that is how you write down an expression, and to check whether the expression is valid or not, you can always substitute k to be the value you found, which is beta z hat for a z directed wave, r can be simply z z hat, and if you take the dot product of the two, you will get e to the minus j beta z, which is the original expression that we had written for the plane waves before. Now that we know this, all right, the problems can be expanded to a variety of things. We can start to look at what will happen at an interface, what will happen if the wave travels at a particular angle to an interface, all right, what happens when it is normal to an interface, etc. So, that is why we are writing down these expressions. We want to understand what a plane wave will undergo if it hits an interface at normal incidence or at some other angles of incidence. We want to be able to write down the expressions. Okay. But just before we proceed, I will also write down a couple of things that will need some thoughts. Okay. So, we have the electric field expression to look like E naught e to the minus j k dot r. Okay. We can always write this down as e to the minus j, okay. K is simply written as beta n hat. Okay. So, you can write this down as beta okay, and you can take the dot product with r. R is x x hat plus y y hat plus z z hat in the most generic form. So, you can take the dot product. So, you can say that beta x cos phi x, okay, and you can have a term e to the minus j beta y cos phi y e to the minus j beta z cos phi z. So, you have taken the dot product, the most generic case, and you have written down, right. Okay. Now, another thing to remember in these cases is similar to your transmission lines. Omega divided by k is phase velocity, right. And suppose I want to find out, so it is represented by say v suffix p, all right. Suppose I want to find out the velocity along z direction, phase velocity along z direction, z component of it. Right. So, I can just write this down as omega divided by kz. Remember that omega is in radians per second, all right. So, it is not a vector quantity or anything, but the denominator is k. Now, we have just now written k to be an expanded vector. It had an x, y and z. So, k is a vector over there. Suppose I want to take the z component of the velocity. The numerator is omega, remains fixed, divided by kz. That would give me the phase velocity along the z direction. Okay. Now, let us look at this a little bit more closely, right. Omega divided by kz. I already know from the previous class, all right, kz is going to be, all right, this part over here, right, right. So, I am going to be having cos phi z, all right. So, I am going to take only the part which is not the vector part. I am going to take the coefficient of the vector, right. So, I am going to be having kz divided omega divided by cos phi z. Oh, sorry. Okay. So, omega divided by beta cos phi z, that will be my phase velocity component in the z direction. Now, if we have to look at this even more closely, omega divided by beta, okay, beta was measured in radians per meter, omega was in radians per second, both of these were constants. Okay. So, omega divided by beta was actually a velocity. Okay. So, and in the strictest sense, this is going to be the velocity in the medium. If you do not consider any direction, etc., this is going to be omega divided by beta was actually how we defined phase velocity, all right, before we wrote down the vector expansion for k, etc., right. So, this means that I am going to be having a velocity divided by cos phi z, okay, just taking the units. Omega is in radians per second, beta is in radians per meter. So, I am going to be having some velocity divided by cos phi z, all right. Now, suppose we think of this medium to be vacuum or air, all right. The value of omega is going to be something, all right, some radians per second. So, you can take a specific wavelength, you can calculate the frequency corresponding to that wavelength, and then you can calculate the omega for that particular wavelength or frequency. Okay. Similarly, you can calculate the beta for that particular wavelength or frequency as 2 pi by lambda, right. Then you can substitute omega divided by beta will correspond to the velocity in free space, which will be 3 times 10 to the power 8 meter per second, okay. And it is divided by cos phi z. Now, one will have to be clear about what we are looking at. Divided by cos phi z means that too many questions will start arising. Cos phi z will go between plus and minus 1, it passes through 0, all right, which means that the phase velocity here, that what we are talking about, can be equal to the bulk velocity that we are talking, right, in the medium, can be infinite, can be positive, can be negative, all right, and there is no limits to what the phase velocity can do, which if you go back to my original discussions that we had about phase and group velocity in one of the lectures, said that we should not be deriving lot of inferences from phase velocity, okay, because it simply does not have any limits. It could, depending upon the value of phi, which is the angle with respect to the z axis in this case, right, it could be positive, negative, 0, etc. I mean, it could be infinity for all we know, right. So, the phase velocity could be any value if you take like this, right. So, it does not convey any meaningful information, right. So, conclusions based on phase velocity should be very carefully made, because it may appear like you will get propagation in one direction faster than the speed of light in vacuum for specific value of phi z. Okay. Immediately questions will start arising as to whether you are doing something wrong with the theory of relativity and all these things. So, one has to be careful. Phase velocity being higher than velocity in free space is not at all uncommon. Okay. Simply by the expressions that we have written, the phase velocity could be higher than the velocity in free space, but it does not mean anything. Okay. So, this is something that one has to keep in mind. We have not yet seen the other type of velocity that is more important. We will be going there slowly. The other meaningful one that people always talk about is what is known as group velocity. It is d omega by dk in the strictest sense, a small change of k giving rise to a small change of omega, and you take the ratio of that, and that actually gives you the group velocity, right. So, group velocity is a more meaningful term where you can draw inferences, okay, and we can write down, so far from what I know, is at least in most of the claims this has not been the case. There have been a few claims about a couple of terms, superluminal propagation, all right, but the publications have drawn heavy criticism, saying that the experiments are not very clear or they need additional proof. So, it is not clear whether they are talking about group velocity or phase velocity, etc. So, even the most experienced researchers could make these mistakes, because experimentally it is very tough to separate things, all right. So, in Google you can have a look at the term superluminal propagation, all right. You will have a lot of hits, and you will have also run into some papers on which there were some tough debates. Okay. It is good to know this, because you will then understand a publication in a journal is not free from criticism even after it is published. So, all right. So, most of the times in very good journals, after it is published is when people start reading. So, you will get more criticism only after that. So, but it is a good article nevertheless, because the rebuttals tell you about group velocity and phase velocity in a broad sense, and why some claims need to be relooked, right. So, you can have a look at superluminal propagation on Google. So, now that we know how to write down the expression for an electromagnetic wave, and also we know the pitfall, that is, if you did get a solution for a phase velocity higher than c, there is nothing to panic, it could actually be the solution to your problem. Now that we know this much, I think we can proceed to the next part, which is dealing with interfaces. Okay. So, there are multiple things that we are going to deal with respect to interfaces. So, interfaces means that you have one medium on one side, another medium on another side, and an interface in between these two media. In transmission line, the equivalent would be you had one transmission line with L and C parameters on one side, and then you had another transmission line that is joined to it. So, it had different L and C, it had different characteristic impedance, it had different absorption coefficient, etc., but they are connected to each other, and the wave travels from one transmission line to another transmission line. So, in this case you are going to be having a wave going from one medium to another medium. We will start with the case which is similar to the transmission line, all right, where we are talking about propagation in such a way that the wave hits the interface normally. This would be the case equivalent to transmission line. Suppose you connected two transmission lines, the direction of travel is in such a way that it hits the interface perpendicular. So, this is a case where it would be very, very similar to transmission line reflection coefficients, etc. But since we have written down the expressions for electric fields in arbitrary directions, there is a difference between the electromagnetic waves and the voltage and the current waves in the transmission lines, that we will see a little later. Also, we know that another difference is polarization. We have not considered polarization in transmission line, but here we have seen circular, elliptical and linear polarization. We have to see what happens to the polarization when the wave goes through an interface. These are the broad objectives. Okay. So, I will start with a setup. The setup here is I am going to take an axis, right. Right. I am taking an axis and direction of travel is along z. Okay. This means that I can take the right hand, y is out of plane, okay, and I will mark medium 1 on the left side, all right. Medium 2 on the right side, okay, and in most generic case medium 1 can have a value of conductivity, permittivity, permeability, and here it could have sigma to epsilon to mu to. All the values could be different or one of them could be different, but the most generic case everything is different. Now, we also need to look very carefully at these interfaces. We are starting with dielectric interfaces. Later on we will see interfaces between dielectric and metal, etc. So, for now I am going to say that let us assume that the conductivity is 0 in both cases. Okay. So, I have epsilon 1 mu 1 on one side, epsilon 2 mu 2 on the other side, right. And I am going to be having a wave traveling going from left to the right, hitting the interface and then something happens. Okay. So, in order to make that clear, I am going to be drawing some vector diagrams. Right. So, I am saying that the unit vector in the direction of k is going this way, all right. So, I am having a wave traveling from left to right. Okay. And now I have to make some assumptions. So, I am going to start with the case where the electric field is oriented this way. Okay. Electric field is oriented this way, direction of propagation is horizontal, which means that using my right hand rule I can figure out how my magnetic field is going to be. In this case it is a right handed system, so the magnetic field is going to be out of plane in this case. Okay. Now, this wave is a plane wave, all right, and its direction of travel is from left to right. It goes, hits the interface, okay, hits the interface. Now, we know that since epsilon 1 mu 1 on one side is different from epsilon 2 and mu 2 on the other side, there is going to be a change in characteristic impedance between the two media. All right. So, already we know from transmission lines that when we have difference in characteristic impedances between the two transmission line sections, you will be having some reflection. Okay. So, there is going to be some reflection and the reflection is also going to be a plane wave, all right, and we have to make some assumptions, okay, in order to proceed further, all right. Now, what we are going to do is we are going to have a reflected plane wave also, and we are going to assume that let the electric field not flip its direction. Okay. K vector is flipped, obviously it is the reflected wave is traveling from right to the left. So, if you were to mark the unit vector for K in this way, you cannot have the same configuration of electric and magnetic fields. Okay. So, if you assume that the electric field is unchanged, right, then you will have to flip your magnetic field, okay, which is the only way it will form a right handed triad. Right. Now, in order to distinguish between these two, we can add some subscripts. I can say that E I corresponding to E incident, H I corresponding to H incident, okay, and E R corresponding to reflected, HR corresponding to reflected. Okay. Let us also make a few more things clear. The point on the left, going to call it as z equal to 0. So, z equal to 0 forms the interface between the left and the right hand side semi infinite media, and the wave is travelling from left to right, gets portion of it gets reflected, and the assumption is the electric field does not flip. If the electric field does not flip, then the magnetic field has to flip. This is one assumption. On the other hand, if you assume that the electric field has flipped, then the magnetic field direction will remain unchanged. Okay. So, that is also one way of looking at it. Okay. Now, the other thing that we know from transmission lines is that you may have some reflection, but for the reflection coefficient to be equal to 1, you needed to have a short circuit or an open circuit. In the case of electromagnetic waves, you needed to have a perfect electric conductor or a perfect magnetic conductor to have a reflection coefficient of 1, which means that if you do not have a perfect electric conductor or a perfect magnetic conductor, you are not going to be having a reflection coefficient of 1 for the electric field. That means that some portion of it is going to be transmitted. Okay. Some portion of it is going to be transmitted. So, now we are going to say that the transmitted wave has no change in the direction of the electric field, or the polarization is fixed. Right. It travels from left to right once again, okay, which means that the magnetic field is going to have similar configuration as the incident magnetic field, and the subscript T stands for transmitted. So, now we are dealing with 3 waves, one which is incident, a portion of it is transmitted, and a portion of it is reflected back, all right. And the incident and the transmitted have similar orientations for the electric magnetic field and the K vector. For the reflected case, the K is flipped, magnetic field is also flipped. Okay. This is the way we are setting up the problem, and what we want to know is the ratio of ET to EI and ER to EI. We want to know what fraction of the electric field is reflected, what fraction of the electric field is transmitted. This is the objective. So, we can start with the expressions for the electric field. Since our coordinate system is very wisely chosen, this is known as normal incidence. So, the interface is like this and your wave is hitting in this way. So, it is a normal incidence, angle of incidence is equal to 0. Okay. Normal incidence means that angle of incidence is 0, because you have to draw a normal from the interface and measure the angle between the normal and your direction of propagation. So, normal incidence, right. So, I am going to say that I am going to write down some expression for the incident electric field. Okay. Let us say that it has some amplitude, right. It has some propagation constant Ax hat. Okay. The electric field is oriented in the x direction, so the unit vector is Ax hat. Okay. It has a value or amplitude of Ei naught, right, magnitude of Ei naught, and propagation constant of gamma 1 corresponding to epsilon 1 mu 1, and in this case we are starting with sigma equal to 0, but still, right, in the generic sense it will have gamma 1. Right. Similarly, we can write down the expression for the magnetic field. This is going to have very similar form, except that the unit vector for the magnetic field is in the different direction, that is all. Okay. By now we are very familiar with how to write these expressions. You can go one step further and say that you can apply Ohm's law for calculating the value of the magnetic field that you have written here. So, you can always write this down as Ei naught divided by the intrinsic or the characteristic impedance of medium 1, which is represented by eta 1, okay, e to the minus gamma 1 z Ay hat. Okay. So, this is how one would write down incident fields. Okay. Now, let us write down the expressions for the reflected field. Okay. So, we are going to be having E suffix r, right, it is going along this direction, right. So, it is going to have some magnitude E r naught. Once again it is travelling through the same medium, alright. So, it experiences gamma 1 z. Notice that the sign is e to the plus gamma 1 z because it is a backward wave, alright, in the way we would traditionally describe from the transmission lines and even from the Maxwell's equations. It is a backward wave, alright, and orientation of the electric field is still the same. We have assumed it to not flip its direction, right. So, it is A x hat. Magnetic field corresponding to the reflected wave is h r naught e to the gamma 1 z, okay. But now it has flipped its direction. So, you just write this as, okay, minus a y hat, okay. Or you could also go ahead and do this as minus E r naught divided by eta 1 e to the plus gamma 1 z. This is how you would write down the expression for the reflected field. Now, we can also write down the electric and the magnetic field expressions for the transmitted part, okay. So, that would be E t of z, it will have some magnitude, right, E t naught. Now, it is travelling in the same direction as the incident wave, which means that you will be having minus z coming into the picture, but it is travelling through a different medium. The medium has a propagation constant, say gamma 2, alright. So, you will have to make that gamma 2 z, alright, and we are assuming that the transmitted field has the same electric field orientation as your incident field, right. So, once again this is A x hat okay, and we can write down the expression for the magnetic field that is transmitted. So, we will be having h t naught e to the minus gamma 2 z and its orientation is the y direction. Okay. So, it is clear that we are launching an electromagnetic wave from the left side and it is of a specific wavelength or frequency, okay, and it is going and striking this interface, part of it is reflected. So, at any given point of time, the total amount of electric field that you will have in medium number 1 is going to be the sum of the electric field that you have launched and the electric field that is coming back. It is very similar to the standing wave case that we have seen in the transmission line, right. So, you will have a sum of the two. In other words, if there is an absolute reflection from this interface, then you will be having perfect standing waves, alright, in medium number 1, okay. But since not everything needs to be reflected, so we can write down the total fields, okay. So, when we talk about the term total field, in medium 1, okay, you can write this down as E suffix 1 is going to be E I plus E r. So, it is a linear superposition of the incident electric field and the reflected electric field, and you can do the same thing for the magnetic field. H1 is going to be Hi plus Hr, okay. So, when you talk about total fields, It's a very common terminology that is used. You are talking about the incident plus the reflected field in that medium, right. In medium number 2, for example, if I want to write down total fields, it is just only one thing that is going. So, it is going to be the transmitted field. So, it is E2 is simply going to be equal to Et, H2 is simply going to be equal to Ht, right. Okay. Now, in certain formulations, when they do simulations, they use this term total field, scattered field formulation. Okay. So, there they are talking about something very specific, all right. We will go through that in subsequent classes, but the terminology is total field means Ei plus Er, and usually when they talk about scattered field, in this case we are considering a pure reflection, scattered field will just be Er. So, in many cases when you place a photo detector in your computer simulation on one side, it will be actually responding to the superposition of the incident and the reflected field. So, people will want to separate the incident field and observe only the reflected field. So, they do some tricks with the equations. Okay. So, when they want to extract only the scattered, only the reflected part, they usually run some tricks or run some algorithms, not exactly tricks, but algorithm to do this, right. And there are very specific ways of doing that, we will be seeing it later. Okay. But the term is very common, total field means that you are considering incident plus reflected. Okay. Now, let us look at this interface. Okay. At z equal to 0. Okay. Now, thus far we have been talking about the two curl equations, all right, and we did not talk too much about the two Gauss's law equations. Then I said that it was implicit boundary conditions for the particular case that we are considering, right. So, we were saying that in the case of electromagnetic solvers where you are using the two curl equations, right, the two Gauss's law become implicit boundary conditions. Okay. So, one has to remember that, and then when you are using it for interfaces, the Gauss's law is very important for you to determine continuity of fields. Okay. Which fields are equal on medium 1 and medium 2, which fields are not equal in medium 1 and medium 2 is actually determined by Gauss's law. So, it is known as a boundary condition or an implicit boundary condition. If you assume your charge density to be equal to 0, it becomes dielectric interface, right. Now, I do not want to elaborate because this should have been done in the undergraduate part already. The tangential part of the electric field or the tangential component of the electric field is continuous. Okay. This comes directly from Gauss's law. This is for a dielectric interface. I am writing H tangential continuous. Okay. Again, dielectric interface, both the fields are continuous, the tangential. Okay. The tangential components are continuous. Is there a problem? Yeah, continuous means in strict sense it is just equal. At that point, whatever is coming here is equal to that, that is all it means. There is no abrupt discontinuity at that point, that is it. So, that does not change sign, does not change value very easily, it is just equal. So, I mean if you want very easily you can write that E1 tan simply equal to E2 tan, that's all it means. And you can write this for the magnetic field also, you can write that H1 tan is equal to H2 tan. So, mathematically that is all it means, continuity. Okay. But to be very clear, we have to write that at position 0, which is the interface. Okay. So, at z equal to 0, plus the reflected. So, you have incident and the reflected at the position 0, okay, has to be equal to T 0. Remember that in this case the electric field is already tangential, the way we have drawn the system. Okay. Your interface is like this and your electric field is oriented upward. So, it is already tangential. So, your total fields in medium number 1 have to be equal on each side. Okay. So, you have incident field plus the reflected field in medium 1, both are pointing tangential, right, both are pointing in the same direction, has to be equal to the field on the right side, that is according to the Gauss's law. So, you can mark this as equation number 1, okay. And you can say that H I of 0 plus H R of 0 is equal to H T. Okay. This is equation number 2, but since it is using another variable, we could always substitute for H I, H R as E I of 0 divided by eta 1 plus E R of 0 divided by eta 1 is equal to E T of 0 divided by eta 2. Okay. Then if you consider that E I, E R, E T are your variables, then you have 2 equations, then one would say that you have 3 unknowns, all right. I mean, then you cannot find out all the unknowns. What is the thing that you can find? We were interested in finding E R divided by E I, E T divided by E I. So, you could divide equation number 1 by E I of 0 on both the sides, all right. Then what happens is you will have the ratio, 2 ratios will be there, then you will have 2 variables. Same way you can divide the left and the right hand side of equation number 2 with by E I of 0, you will end up with ratios, you will have 2 variables. Then you will have 2 equations, 2 unknowns, and then you can solve for the unknowns, which would be E I by E 0 and E R by E I and E T by E I, sorry. Okay. So, 2 equations, 2 unknowns, straightforward to solve. So, what happens is it looks exactly like what you had in transmission lines. Okay. ZL minus Z0 by ZL plus Z0 is what we had in transmission lines. It looks exactly like the reflection coefficient in the transmission line. So, for the normal incidence on an interface, all right, when you are assuming that there is no flip in the electric field and all that, it seems like it is exactly analogous to transmission lines. So, it is fine for you to assume that everything is a transmission line and then the join pieces together and you may arrive at the similar deductions, right. But one of the things that we had not seen when we were dealing with transmission lines was actually, we had not seen this at that time, right. We had seen only the reflection coefficient. Here we are also considering a transmission coefficient because these are semi-infinite media and you will have propagation on the right side in that media also, right. So, you can always take E T by E I. We did not do this for transmission lines, but we could always do it. Okay. So, here it turns out to be 2 times eta 2 by eta 2 plus eta 1 all right. So, the first term or the first boxed expression is called gamma, similar to your transmission lines, is just the reflection coefficient. So, if you have an interface between 2 media, eta 2 minus eta 1 by eta 1 plus eta 2 is your reflection coefficient. Straightforward, transmission coefficient is represented by tau. Okay. In the case of transmission line, tau represented transit time, but here it just represents transmission coefficient. Okay. There are also some other relationships that one can find out between gamma and tau. Okay. So, since the denominators are equal, eta 1 plus eta 2, you could just take a sum and see what happens, all right. you could take eta gamma plus tau is what, or 1 plus tau is what, 1 plus gamma is what. We can always try to see the relationship between gamma and tau, alright. You could simply say what is gamma minus tau and see what happens, right. So, there are a variety of things that you can do, because the denominators are equal, you can always add, subtract and see what happens, but you can also find out a straightforward expression between gamma and tau. So, it will look like 1 plus whatever is your gamma will look like tau. 1 plus gamma is tau, okay. Now, this raises some important questions. 1 plus gamma is tau, alright. 1 plus some quantity is your transmitted electric field. Now, remember that we are still talking about electric fields, just like in the case of transmission lines. When we talked about reflection coefficient, we were clear that we were talking about voltage reflection coefficient. We did not talk about current reflection coefficient a lot. Okay. We just said that the current reflection coefficient was negative of the voltage reflection coefficient. Here we are talking about electric field reflection coefficients. Okay. So, most of the time when we talk about reflection coefficient, it is about the electric field, and for the electric field reflection coefficient in this configuration, what we have considered, 1 plus gamma is equal to tau. Now, this needs a lot of thought, okay, needs a lot of thought, because it means that your incident electric field could be say 1 volt per meter, your transmitted electric field can be higher than 1 volt per meter, okay, it is not uncommon. So, it is perfectly possible for you to have electric field in the second medium higher than the incident electric field, and it is not an absurd solution at all. One can always ask a question, then how is the energy conserved in this kind of a system, alright. The answer lies in the magnetic field. If electric field will go up, magnetic field will go down and adjust in such a way that there is no energy loss or no energy created in this system, okay. So, if you get a solution where your transmitted electric field is higher than the incident electric field, you need not panic, it could be a valid solution. It may need some verifications whether the magnetic field is decreasing by the same amount, etc., but it is possible. So, you can have transmitted electric field to be higher than the incident electric field, it is not uncommon. So, this is something that you have to keep in mind. Typically, gamma is complex, 1 plus gamma, obviously tau is also complex, okay. We know that from our transmission line that gamma is going to be complex, it will end up having a real and an imaginary part, alright, which means that 1 plus a complex number is again you are going to be ending up with a complex number, okay. So, tau is also going to be a complex number, okay. You can also do some validity tests with this and try to see what happens, but a more rigorous approach would be better, but just for the sake of completeness, I would just do a simple thing, alright. If there is a scenario where the first medium okay, is having no conductivity, but obviously characteristic impedance is not 0, and suppose we say that sigma 2 is equal to infinity, okay. Directly you need not approach this problem, we just want to see whether our equations are holding good for this case or not, alright. Otherwise, you could write down the same thing, you could write the incident field, write the reflected field, write the transmitted field, try to find out the value of gamma and tau using proper boundary conditions, okay. Then you will find out that you are having a case where sigma is equal to 0 on one side, sigma is equal to infinity on the other side, okay. We can guess, right, gamma is equal to minus 1, alright, corresponds to this case, alright. Sigma equal to infinity, that means you have a perfect electric conductor, and when we ran a simulation with our codes, alright, we had written the Maxwell's equation in one dimension, and we had written a code. Suppose we make one side to be a perfect electric conductor, which means that you make the electric field equal to 0. Whatever be the voltage, you will not get an electric field over there. Okay. So, if you do that, then you will get a reflected wave which is flipped. Alright, we saw that an impulse will travel, it will get flipped in direction and then it will come back, etc. So, gamma is equal to -1. Alright. Consequently, 1 plus gamma is tau. We can make some inferences that actually tau is 0. So, if you have a wave that is trying to penetrate into a perfect electric conductor, that is not going to be possible. Okay. Any wave is not going to be able to penetrate into infinitely conductive medium, right. So, we say that tau is equal to 0, gamma is equal to -1, 1 plus gamma is equal to tau for this particular configuration. One could also write down the electric field in medium number 1 to be equal to EI plus ER, right. So, you are going to be having an incident field. Let us say that EI naught e to the minus gamma 1 z plus you are going to have ER naught e to the plus gamma 1 z, and they are going to be oriented along the x direction. Okay. Now, we know what this is going to be, alright. You are having E naught minus gamma 1 z, E naught plus gamma 1 z. If you assume that sigma 1 is equal to 0, then they will simply become e to the minus j beta 1 z, right. So, you will have EI naught e to the minus j beta 1 z plus ER naught e to the plus j beta 1 z. We can also say that EI naught e to the minus j beta 1 z and ER naught, okay, is gamma times EI naught. So, you can write this as minus EI naught okay. So, you will end up getting a difference between two complex sinusoids, right, and the result will be minus 2j EI naught sin beta 1 z x hat. What this is telling you is that in medium number 1, suppose all of the electric field is reflected back, you will be having a superposition of the incident and the reflected electric field, and the superposition is such that it is going to create a standing wave, alright. It is going to create a standing wave in medium number 1 at some positions z in medium number 1, you will be having 0 electric field, at some other positions you will be having maximum electric fields, but they will vary only with respect to time. With respect to the space, in certain places you will be having 0 electric field. So, this is the same as what we had seen in transmission line. If you in fact you go back and see the expression, it will be identical for a short circuit condition, right. So, this is minus 2j v sin beta z is the expression that we had for the net total voltage present in the transmission line for a specific boundary condition, short circuit boundary condition. So, this will look exactly the same, alright. So, this means that you will be having a total wave in medium number 1 to look like having nodes and antinodes. So, in other words, you will be having standing waves in medium 1, and these, because the reflection coefficient is magnitude is equal to 1, it is a perfect standing wave, means that the node is exactly 0, okay, minimum is 0, right. If it is not equal, then you will not have the forward and the backward wave cancelling each other completely. It will not be a 0, you will have some different voltage standing wave ratio in the case of transmission line, you will be having a different standing wave ratio in the case of electric fields, okay. But I have done this, alright, without changing the boundary conditions and all that, just to look whether there are sanity checks. One has to be aware of all the boundary conditions possible and then use the correct boundary conditions to arrive at the same or similar expressions, okay. So, I think we will stop here. The next thing what we are going to do is simply see how this problem changes when we have the wave going at an angle with respect to the interface, complete that. Then we will go to the metal dielectric interfaces oblique and normal, alright. and then we will start to look at what happens to polarizations, etc. Right? What are the consequences? Here we have assumed the electric field to just do this, right? Suppose if it is circularly polarized, suppose if it is elliptically polarized, etc. What would happen? Okay, so we will see about that. In specific, we are going to be dealing with what are known as Fresnel reflection coefficients for different polarizations, and what are the consequences and what are the inferences from these two. We'll stop here.